Welcome to the week 6 of the Introduction to Advanced Machine Learning webinar series, and thank you for joining us today. In this webinar about neural networks, the theory portion of it would be taken care of by me, Sneha, and the second part, implementation of neural network, would be taken care of by Rishika. I'm excited to introduce the concepts and give you a strong foundation on neural networks for the next 2 hours. But before we begin, let's start with some announcements. A huge shout out to our amazing team of leaders and volunteers for putting together this series. It has been a wonderful journey, and I thank all the participants as well for making this a huge success. In this session, Rishika and I will be the speakers, and all the other leaders will be present on chat to support you. Feel free to reach out to us with any questions you might have. Our panelists will share more information on that in the chat. And a huge shout out to our sponsors, Home Depot, for putting together much needed events for the community amidst the quarantine. Do show your appreciation for them by retweeting our post, and one of our panelists will be sharing them in the chat as well. Before we begin, a quick roundup of the things you need to kickstart today's session. So starting with the slides, they are all present in this URL. One of our panelists will be sharing this information in the chat. Feel free to download and follow along. If you have any questions regarding today's session, post them in the QA box, and one of our experienced panelists will answer them during the session. If you're facing any issues during this webinar, do chat directly with the panelists to help you out. If everything is working for you, please give a thumbs up and we can get right into the session. Oh, also, please don't forget to follow us on the social media platforms and LinkedIn. Also join our Slack channel for our next event updates. This information will also be shared with you in the chat. We are in the final week of the series, and here is a small recap. We started the sessions with K nearest neighbors, and then we went on to some cool unsupervised machine learning models like clustering, outlier detections, dealing with text data, and time series analysis. And to mark the finale of the series, we'll be talking about neural networks today. All right, let's get straight into it. In today's session, we will start by understanding the basics of neural network, a brief introduction, a little bit of history, and then we will talk more about it, and then we will dive into the structure of a single neuron. It is called a node in artificial intelligence. The different components that are part of a complete artificial neural network, and then we will talk about feed-forward function, which is how the information is passed from one neuron to the other. And then we will talk about backpropagation and gradient descent, which are important methodologies to optimize your neural network. So by then, we will know how a simple neural network functions and its various components. After that, Rishika will take over and talk to you about how to implement a neural network using Google Colab. So let's start with a basic question. What is neural network? Simply put, it is a software implementation of the neuronal structure of our brain. So let's see how our brain works first. The brain is a hugely interconnected network of neurons, and each neuron is connected to thousands of other neurons. So the input of one neuron may be taken as, the output of one neuron may be taken as input by 1,000 other neurons. And learning occurs by repeatedly activating certain neurons over others. And thus, we are able to perceive things like spotting a balloon in the sky or smelling something nice. Similarly, the artificial neural network attempts to mimic this behavior and gives us various answers based on underlying patterns detected by these neurons. Now let's try translating that into a problem. Let's say you are building a model to track fitness, and let's say you have the speed data of a person. Now, when we are assessing their activity, let's say they are going to their office by walking. Now you know if the person walks in X speed, then the person is walking, and we write an algorithm to track that, and we can track how many calories are being burned. Now let's say we need an algorithm for running, and then we say, okay, if this person goes in this speed, then the algorithm can track their running. And now we have more code in our algorithm to identify that. Now let's say we get more data, like the heart rate. Now we try adding one more algorithm that identifies biking. That's when the heart rate is at some point and your speed is at some point. Now you want to write another code for when the person is swimming. Now this might be efficient for this one person, but imagine hundreds of users for your fitness app. In that case, there has to be many rules and heuristics that has to be applied to make your model more efficient. And it is extremely difficult to keep on adding new activities and users. And this is where neural networks come into play. Instead of trying to define the rules or understand the underlying pattern, in neural networks, we typically provide the answer along with the data. And we tell the machine to infer the rules that determine the relationship between the answers and the data. So to reiterate the definition, a neural network is an interconnected group of neurons or nodes that uses a mathematical or computational model for informing processes to determine the underlying pattern that leads to the desired output. Cool. Now, before we dive deep into the structure of the neural network, let's look at the history of neural networks. So the preliminary theoretical base for neural networks is present in the 1800s, but it is not until 1950 that a physical neuron or node or perceptron was built. Rosenblatt is the scientist who implemented the idea of the perceptron in a custom hardware and showed that it could be used to learn to classify simple shapes. And thus, this part of machine learning was born. A computer was built that could approximate a function given known inputs and outputs. Soon enough, backpropagation was discovered by multiple researchers in the 60s and implemented to run on computers as early as 1970s. You can see in the side image here how a physical perceptron looks like in the 1950s. After that, around 1970 is where many skepticism around the limitations of a perceptron was observed. And slowly, many researchers call this approach of AI a dead end, and it slowly lost interest. Again, around 1980 is when multi-layer neural networks was uncovered, and the topic was once again hot in the market. This is where the start of understanding the potential of a neural network was slowly discovered. In 1989, AT&T Bell Labs demonstrated a very significant real-world application of backpropagation to analyze handwritten zip codes. This sparked so many interest, and this is a project that we still have so much value. And if you're a beginner, it is one of an important project to have in your portfolio. But again, around 1990s, support vector machines and random forest beat the neural network models in compute power and time efficiency. Again, neural networks was losing hope. In the meantime, there were many questions around neural networks of like how to apply probabilistic models. Can we use it in unsupervised machine learning? Instead of varying weights, can we vary the rewards? And that is how reinforcement learning, recurrent neural network, speech recognition, and all of those fields came into existence. And all of these advancements happened closer to 2000. So with support vector machine and random forest proving high accuracy over neural networks, the early 2000s saw a decline in the neural net research. But there were research in machine learning and in the field of AI still actively happening. but it needed something more to get back into the market. And that is with the discovery that efficient use of GPUs and computing power in general was so important for faster computation, made people re-examine the longer held assumptions and failures with neural networks. That's how deep learning got the attention of many. And with the evolution of big data, cloud computing, neural network got precedence again for being effective with large data and also because of the rapid increase in computation power. And now here we are at 2020. AI as a field is huge and still moving forward. And we are expanding outwards in terms of varied applications of neural nets and deep learning. And for good reason, deep learning still works best only when there is a huge data set, which is not true for many problems in the real world. And this brings us to the pros and cons of neural network. Neural networks are flexible and can be used for both regression and classification problems. Any data which can be made numeric can be used in the model. As neural network is a mathematical model with approximation function, any data which can be made numeric can be used in the model, as neural network is a mathematical model with approximation function. Neural networks are good to model with nonlinear data with large number of inputs. For example, images. As you know, each pixel of an image becomes an input feature for a neural network. And neural networks can be trained with any number of inputs and layers. It is a reliable approach for tasks involving high dimensional features. And neural networks work best when there is a large amount of data. One of the things that increased the popularity of deep learning is the massive amount of data that started getting available around 2018. This enabled neural networks to really show their potential since they get better with more data. In comparison, traditional machine learning algorithms will certainly reach a level, but with more data doesn't mean it improves their performance. Now, to look at a few cons, neural networks are black boxes, meaning we cannot know how much each dependent variable is influencing each independent variable is influencing the dependent variable. You don't know how and why neural network came up with a certain output. For example, when you put in an image of a cat into a neural network and it predicts it to be a car, it is very hard to understand what caused it to come up with this prediction. Like the recent news of a picture of, like the recent news of a picture of onion being classified as sexual. You can only speculate the reasons behind, but you cannot confirm the math behind why the neural network came up with this answer. So when you have features that are human interpretable, it is much easier to understand the cause of mistakes. In comparison, algorithms like decision trees are very interpretable. This is important because in some domain, interpretability is quite important. Usually, neural networks are also more computationally expensive than traditional algorithms. State-of-the-art deep learning algorithms can take several weeks to train. Most traditional machine learning algorithms will take as much as a few minutes to few hours or days. Hence, we need to choose neural networks usually require more data than traditional machine learning algorithms, as in at least thousands, if not millions of labeled data. Great, now you know that neural networks are great for some tasks, but not as great for others. On top of that, you have learned that neural networks can beat nearly every machine learning algorithm, but there are disadvantages that go along with it too. Of all this, an important question always remains unanswered. If neural networks are supervised machine learning models or unsupervised machine learning models, Do you guys know the answer to this? If so, can you please type in the chat? And I would like to see what category you think it falls in. I'm seeing a mix of answers of both unsupervised and supervised machine learning. Neural networks are can be both supervised and unsupervised machine learning based on the problem. In a supervised machine learning model, in a supervised neural network, the network is trained by providing matched input and output data samples with the intention of getting the neural network to provide the desired output for a given input. In unsupervised learning, there is an attempt to get the neural network to understand the structure of the provided input data on its own. This is applied in topic generation in text data and classifying images most of the time. So yes, it can be a supervised or unsupervised machine learning model based on the use case. Cool. Now that we had a good introduction, let's move on towards building a neural network. First, we will jump into the structure of a neuron. In artificial neural networks, a neuron is usually called as a node. Let's compare that to a natural neuron. We don't need to talk about the complex biology, but we can say that the complete brain is hugely connected with networks of neurons, where the output of one neuron may be an input to thousands of other neurons. The brain contains thousands of neurons, which are like switches that are activated based on the strength of their chemical input. This makes them more likely to produce a desired outcome given a specified input. Also, this learning involves feedback. That is, when a desired outcome is reached, the connection that caused that outcome strengthens and vice versa. Artificial neural network attempts to simplify and mimic this brain behavior. Let's take for an example, a spam filter. Suppose we look at an email visually with our eyes and we look at the various words in the body of the email and our brain gives us a signal that it is a spam. So when another email with similar words pop up, your brain can immediately identify it as a spam. Similarly, if many examples of emails are passed through the neural network, this allows the neural network to learn what input data makes it likely a good email or a spam. This learning takes place in the neural network by adjusting the weight, the bias, and activating the neuron based on the activation functions. We will look closely into all these parts of the neural network: the node, the weights, the bias, and activation functions. These are the four things that form a structure of an artificial node. The first thing is the node. As mentioned previously, each biological neuron can be referred to as a node in artificial neural network. It is sometimes referred as an artificial neuron or perceptron in some books and some tutorials. Each node takes multiple inputs, their weights, and apply an activation function to the summation of these inputs and generates an output. The circle in the image represents the node in which the activation function resides. It takes an input x1, x2, x3 here, along with their respective weights, sums them, and then inputs them into an activation function. The output of the activation function is shown here as h, where it is a function of x, which are inputs x1, x2, and x3. The next is the weights. Weights are real valued numbers that are multiplied by their respective input parts and then summed up in the node. Here in this equation, Wi is the weight assigned to the input xi. So W1 is assigned weight of X1, W2 is assigned to X2, and W3 is assigned to X3. An important question to ask here is, what are these weights all about? Well, they are the variables that change during the training phase of the algorithm. So as the neural network learns, the weights are altered in each phase before assigning to the inputs to determine the output of the node. And here there's one more term, the B, which is the weight of the bias. The inclusion of this bias enhances the flexibility of the node. What does that mean? Why can't we just have the weights? A simple way to understand bias is by thinking about the linear function. Y is equal to mx plus c. In linear function, if the constant c, which is the if the constant c is absent, then we know that the line will pass through the origin no matter the change in y and x. And you will get a poorer fit because the line cannot move away from the origin. Bias is just like that intercept. It is an additional parameter in the neural network, which is used to adjust the output along with the weighted sums of the input to the neuron. Moreover, bias value allows you to shift the activation function to either right or left. Note that bias units are not connected to any previous layer. It is just appended at each hidden layer and is not affected by the values in the previous layer. We will talk a little more on this. So let's take a very extremely simple node with only one input and one output. So the input to the activation function of the node in this case is simply X1 and W1. So what does changing W1 do in this simple network? You can see that the weights here are changing between 1, 0.5, and 2. And this affects the activation functions correspondingly of 1, 0.5, and 2. Now let's plot that in a graphical way. Here you can see that changing the weight changed the slope of the sigmoid activation function. Let's assume that we use sigmoid activation function here. So, which is obviously useful if we want to model different strengths of relationship between the input and output variable. However, what if we only want the output to change when x is greater than 1? You can see here, x is always passing through 0, which makes it difficult to change that relationship. So that is where bias comes in. Let's consider the same network, but with a bias input. In this case, W1 has been increased to simulate a more defining turn-on. As you can see, by varying the bias weight, you can change the node's activation limit. Therefore, by adding a bias term, you can make the node simulate a generic if function. That is, if x is greater than threshold, then 1, else 0. So without a bias term, you will be unable to vary that threshold. It will always be stuck at 0. This is obviously very helpful if you're trying to simulate conditional relationships. Cool. Now that we know that an input to node contains weights and added bias, let's look at the activation function. Activation functions are useful because they add non-linearities into neural networks, allowing the neural network to learn powerful operations. If the activation functions were to be removed from a feed-forward neural network, the entire network could be refactored to a simple linear operation, and it would no longer be capable of performing complex tasks such as image recognition. Two common used activation functions, the rectified linear unit and the logistic sigmoid function. The ReLU has a hard cutoff at 0 where its behavior changes, while the sigmoid exhibits a gradual change. Let's look at each one of them in detail. The main reason why we would use a sigmoid function is because it exists between 0 to 1. Therefore, it is especially useful in models where we have to predict the probability as an output. Since probability of anything exists only between the range of 0 and 1, a sigmoid is the right choice. The logistic sigmoid function, although has a drawback, that it gets stuck at the training time, which means you would not get an optimal answer. So in those cases, the softmax function is used, which is a more generalized logistic activation function. The next function is the tanh function. The tanh function is very similar to sigmoid. The only difference is that it is symmetric around the origin. The range of values in this case is from -1 to 1. Thus, the inputs to the next layer will not always be of the same sign. Both tanh and logistic sigmoid functions are used in feed-forward networks, but unlike sigmoid, its output is zero-centered. So in practice, the tanh nonlinearity is always preferred over sigmoid nonlinearity. But for general problems, sigmoid activation function is preferred. The next one is rectified linear units. Despite its name and appearance, it's not linear and provides the same benefit as sigmoid, but with better performance. The ReLU is the most used activation function in the world right now, since it is used in almost all convolutional networks and deep learning. So as you can see here, the ReLU is half rectified, which means the function is 0 when z is less than 0, and the function is equal to z when z is above or equal to z. For the negative input values, the result is 0. That means the neuron will not get activated. Since only a certain number of neurons will get activated using this function, the ReLU function is far more computationally efficient when compared to the sigmoid and tanh function. And the ReLU function still has a disadvantage that during back propagation, the weights and biases for the nodes that were not activated might not get updated. And this creates dead neurons. And that is where modified versions of ReLU come into play. You can learn more about it in other tutorials. And despite that, ReLU is the most used activation function right now. Right. So as you can see, it is just a function that you use to get the output of node. It is also known as transfer function in some books and tutorials. It is used to determine the output of neural network, like yes or no, and it maps the result values in between 0 or 1 and -1 to 1 based on the function that we use. So we understand that using an activation function introduces an additional step at each layer during the forward propagation. Now, the question is, if the activation function increases the complexity so much, can we do without an activation function? And imagine a neural network without an activation function. In that case, every neuron will only be performing a linear transformation on the inputs using the weights and biases. Although linear transformations make the neural network simpler, this network would be less powerful and will not be able to learn the complex patterns from the data. Thus, we need to use a nonlinear transformation to the input. And this nonlinearity in the network is introduced by an activation function. Cool. Now, hopefully the previous explanation has given you a good overview of how a good node in a neural network operates. However, as you are probably aware, there are more than one node interconnected in a fully fledged neural network. These structures can come in a myriad of different forms, but the most common simple neural network structure consists of an input layer, which is usually the features, a hidden layer or more than one hidden layers, and an output layer, which is the expected outcome. An example of such a structure can be seen in the screen, and it is a fun yet informative GIF that I found online. And I think this will help you in imagining a neural network better. So the input here is the structure of fruits. So they will be considered as the different features. And there are three hidden layers in the middle that contains nodes. And each node is equipped with an activation function, and there's different weights and biases coming in. And only the respective nodes are activated, and based on those activation, the classification is made of if the fruit that's incoming is an apple or not an apple. Cool. Now let's translate that into a very well-constructed neural network here. So this is an image where there are three layers of the network, and layer one represents the input layer, where the external input of the data enters the network. And we can see that there is many nodes here. And layer two is called the hidden layer, as this layer is not part of the input or the output. This layer contains 5 nodes. Note that neural network can have many hidden layers, but in this case, for simplicity, I have just included one. Finally, layer 3 is the output. You can observe that many connections between the layers. As you can see, each node in L1 is connected to every node in L2, and each node in L2 is connected to every node in L3. Each of these nodes will have an associated weight, and each of these layers will have associated biases. The information moves forward from one node to the other. If you remember the functioning of neurons, the output of one node is given as the input to many of the other nodes in the next layer. And this is the basis of forward propagation. Now let's look at a mathematical notation for forward propagation. Let's simplify that structure even a little more. So here you can see that there are 3 inputs, x1, x2, and x3, coming in on layer 1 into 3 nodes in layer 2, which is the hidden layer. And there are 3 respective functions, activation functions calculated, h1, h2, h3. And then these are fed into another single node in layer 3, and another h1 function is calculated here. So you can see that there's a superscript that denotes the layer that the activation function belongs to. Now we need to calculate h1, h2, h3 for layer 2, and then finally h1 for which is our output in layer 3. The math requires some fairly precise notations so that we know what we are talking about. We know that each function h is an activation function. So that is represented as f here. It can be a sigmoid, ReLU, or any other function we discussed. Each activation function takes as input the output from the previous node, their respective weights, and the bias term. So the notation I'm using here to mention the weights is Wij, where I refers to the node in the layer L+1, and J refers to the node in layer L. And the number in brackets indicate the incoming layer. So let's take, for example, the first weight term. So it's W11 with a superscript of 1. The superscript denotes that it is an incoming layer from layer 1. And the W11 represents going to the first node in layer 2 from the first node in layer 1. And that is how it is represented in most of the books, the mathematical notation. So let's say for W12, it is represented as the node that is incoming to layer 2, node 1 from layer 1, node 2. So it is sort of in the reverse order. I will give like a minute for you guys to observe this. And similarly, the weights for each of them is represented. Cool. Now let's look at a simple problem. And if you have a pen and paper, now would be a good time to get them ready so we can dive into this simple problem. So we have the neural network here, the mathematical notations here, and let's say there is an incoming values of this, where X has 3 inputs. X1 is 1.5, X2 is 2, and X3 is 3. And we have weights for each node represented as this. So this would be X1, X2, X3 for the first node. This would be X1, X2, X3 for the second node. This would be X1, X2, sorry, W1, W2, W3 for the third node. And then the bias. So how do we calculate H1? And I will solve this for you saying, okay, so it is a function of 0.2, which is the first weight, which is going towards the X1 here. So 0.2 multiplied by 1.5 plus 0.2 here multiplied by 2.0, which is the second input, plus the third weight, which is 0.2 multiplied by 3, plus the bias term here, which is the B. And this is how you write H1. Now take your time in writing H2 and H3 for the first layer. So layer 2. And in the meantime, I will answer this question by Nishrin. A single bias is applied to a layer, that is all inputs in a particular node, not different biases. Yes, weights are assigned to nodes while a bias is assigned to a layer. So each layer would have only one bias, if that answers your question. Perfect. We have started getting some answer coming in. So let me go ahead and show the solution. So H2 would be this. It's simple and straightforward. The second row of weights assigned to the inputs X1, X2, and X3, and then this. So based on this activation function, the final output would be calculated, which we cannot do right now, but you can see it's a simple, straightforward calculation. Cool. Now we will move on into understanding the feed-forward neural network more. So we have two layers, the input layer and the output layer, which are important. And then we have two hidden layers, which is where the activation function resides and there's calculation happening. And we know that every network is connected to every other node. Sorry, every node is connected to every other node in each of the layers. And let's say we have a simple classification problem where we are saying, okay, there's an incoming image and we want to classify if that image is a triangle or a square or a circle. Now our inputs are our inputs are the features of these images, and our output would be any one of these three classes: a triangle, square, or a circle. Cool. And now we will have random weights and biases assigned to each of these inputs, and it will calculate the respective activation functions. And based on the value of the activation functions, a few neurons would be activated. And this moves forward into calculating a few other activation functions in the layer, in the next hidden layer. And this will activate a few other neurons, which in turn will predict the output. In here, it is a classification problem. So there are 3 probabilities, and the highest probability of 45% is assigned to a square. So that is how the forward propagation works. Now wait, what if we tell you that the incoming image was a circle? In that case, the given answer by the neural network is wrong. So how do we optimize this to give the right answer? And that's where gradient descent comes into play. So as we said, everything depends on the weights. Now, how do we know how to vary the weights given an error in the output? We cannot calculate the perfect weights for a neural network. There are too many unknowns. Instead, the problem of learning is cast as an optimization problem. An algorithm is used to navigate the space of the possible sets of weight the model may use in order to make a good or good enough prediction. In this diagram, we have a blue plot of the error depending on a single scale weight W. The minimum possible error is marked by the black cross here. And we don't know what weight will give that minimum error. We start out at a random value of W, which is given here in the red dot and marked as 1. One of the most common ways to approach this value is gradient descent. And to proceed with this method, first, the gradient of the error with respect to W is calculated at 0.1. For those who don't know, the gradient is the slope of the error curve at that point. It is shown in the diagram as a black arrow, the slope. The gradient also gives directional information. The higher the magnitude of the gradient, the faster the error is changing at that point with respect to W. The gradient descent method uses the gradient to make an informed step change in W to lead it towards the minimum of the error curve. This steps change is called the learning rate. So the gradient descent algorithm seeks to change the weight so that the next evaluation reduces the error, meaning the optimization algorithm is navigating down the slope as shown in the picture. Now, this is an iterative method that involves a number of steps. And this formula is used to assess the weight in each iteration. So here W new denotes the new position, and W old denotes the current or old position, and delta error is the gradient of the error at W old, and alpha is the step size that will determine how quickly the solution converges on the minimum error. See, the amount that the weights are updated during training phase is referred to as the step size or the learning rate. So specifically, the learning rate is a configurable parameter which can be between 0 and 1. It's a hyperparameter that can be configured between 0 and 1. So during training, the backpropagation of error estimates the amount of error for which the weight of a node in the network is responsible for. Instead of updating the weight with the full amount, it is scaled by the learning rate. As this iterative algorithm approaches the minimum, the gradient or change in the error with each step reduces. And generally, a large learning rate allows the model to move faster, but at the cost of we will arrive at a suboptimal answer. So it is important, a smaller learning rate may allow the model to learn more optimal but it might take significantly longer time to train. So it is important to find a good value for the learning rate for your model in the training data set while training your data set. And the next important thing or hyperparameter to know is epochs. So the number of epochs is a hyperparameter that defines the number of times that the learning algorithm will work through the entire training data set. One epoch means that each sample in the training data set has had the opportunity to update the internal parameters once. You can think of it as a for loop, and the number of epochs is traditionally large, often hundreds or thousands. But in literature and tutorials, you will see an epoch of 10, 50, or 100. And then to seek to minimize the error, we need to calculate the loss. And this is called a loss function or cost function. And the value calculated by the loss function is referred to as loss. So the cost function reduces all the various good and bad aspects of a possibly complex system down to a single number, a scalar value, which allows candidate solutions to be ranked and compared. In calculating the error of the model during the optimization process, a loss function must be chosen to calculate that error that we talked about 3 slides ago. So in case of, so what loss function to use? So given the input, the model is trying to make prediction that matches the data distribution of the target variable. Under maximum likelihood, a loss function estimates how close is the distribution of predictions made by the model matches the distribution of target variables in the training data set. In the case of regression problems where a quantity is going to be predicted, it is common to use mean square error. And a problem where you classify an example as belonging to one or more than two classes, cross entropy is used. Cool. And now we know how to calculate our loss function. Now let's go back to our problem where we gave an input as a circle and the feed forward propagation found that it is a square. So we know that it is wrong. So what now happens is we will calculate the loss for all these 3 outputs. And this loss is propagated back, and this is called back propagation. So this loss will be propagated back to each of the nodes, and with that, different weights and biases will be calculated based on the step function or the learning rate. And then new activation functions would be generated, which will activate different neurons. And this in turn will activate other different neurons by calculating new activation functions. And this right now is one epoch, that is one iteration is complete. And as you know, epochs are usually in ranges of hundreds and thousands. So this happens in the feed forward and back propagation happens about 100 times, or how many ever times the epoch is set to identify or optimize your algorithm to identify the right output. And that is how a neural network is very efficient, and it can go through this iterative process to determine the optimized output. Cool. Now we are in the last set of decks. So we talked about the structure of a node, and then we talked about the structure of neural network, and we talked about how to optimize the neural network to give the right or the efficient output. Now, we need to evaluate our model, which can be a little tricky for neural networks. So we use loss to diagnose model optimization, but we need a metric to evaluate and choose models in the context of project. So the same metric can be used for both concerns, but is more likely that the concerns of the optimization process will differ from the goal of the project, and different scores will be required. So it may be desirable to choose models based on metrics instead of loss. So this is a very important consideration to do, as the model with the minimum loss may not be the model with the best metric, which is important when you deploy your project to real world. Hence, when evaluating model, you have to choose the right metrics based on the problem being solved. So here are some nice metrics based on the problem you might have in hand. So if it's a regression, it's important to use mean square error, root mean square error, or R squared. Well, it's a classification. You can use accuracy, which can be both loss function and a metric. You can also use precision recall and ROC-AUC curves. And for unsupervised models, you can use the RAND index or mutual information. And for other complex networks, there are other scores that are listed here. So once you evaluate your model is when you know if your model is ready to be used in real world scenarios. And with that, we will be getting to the next part of this session, which would be a code along, and Rishika would take over from me and go over a notebook she has put together. In the meantime, I just want to point you to a few resources that I've linked here. One is a YouTube class, and then a beginner's introduction book. And yes, thank you for joining us today. We hope this content was helpful, and if you're learning, I hope this content was helpful in your learning journey. We would like to have your continued support as we give more events and more engaging community is what we are looking for. So if you have any questions going forward, do join us on our Slack and post your questions. For those who attended all the 6 sessions, you'll be receiving a participation certificate within the next 10 days. And don't forget to flaunt the success over social media. And thank you. And we will take a 5-minute break. And within that time, I think Rishika will be taking over my computer. Thank you.
Thanks, Sneha. Yeah, so as Sneha mentioned, we'll take a 5-minute break right now, and then I'll get back to it with the collab coding portion. So for me right now, it's 12:53. So let's just come back at 12:58, and then we'll get started with some coding. All right. Hi, everyone. So that's our 5-minute break. And so the link for the code has been shared. If you click on that link, it'll redirect you to our GitHub repository for this entire series. So you can see all the previous sessions, slides and codes and recordings as well. So this is today's session. And so to open up the notebook in Colab, what you can do is just do a Google search for Colab. And then, so all you need is any Google account. And then we're going to be using a GitHub URL to open this. So the way we do that, let me just move the screen around. So what you actually want to do is, from this link here, you want to just take GitHub. I can make this simpler. If you just go back here and click on Women Who Code Data Science, this is the URL that we want to copy. So if you just copy that link and then move back here, and then we just paste it here and then press search. And then this should show us all of the previous notebooks and everything from the Intro to Advanced Machine Learning series. So if you scroll on down, you can see the one for today, which is number 6, which is for neural networks. So if you just click on that, then it should open up the notebook and you should be good to go. So hopefully everyone is able to get to this stage. Please let us know in the chat or the Q&A if you are having any issues, but hopefully everyone is able to open this notebook and then we can get started. So today, for the data set I've chosen is actually a Zillow home value prediction. It actually is coming from a Kaggle competition, which is a very popular website that hosts competitions, typically where you have some sort of data set and there's an associated task with it. And so the task is basically trying to predict the value of homes that are in this data set that was provided by Zillow. So for more information on the data set, you can click on this link. But what we'll be using today is the link that you see here, which contains the data set itself. So when you click on that link, it should open up to this CSV file in your browser itself. And what you'll want to do is actually download this by clicking on this downward arrow here. And so once you download it, please make sure to save it to a location that you'll remember, because we'll actually we will be having to then upload it to our notebook. So I typically save it in documents or desktop, something like that, just so you remember where you've saved it to. So once you've saved it, so once you download it, it's not too big of a file, so it downloads pretty quickly. And then you can just click on that file itself, and then it'll open up in your on your system. And then just make sure to save it to, as I said, some very easily accessible location. And so from here, what you want to do is in this, typically when you open this up, you'll see this left navigation pane. So this is a table of contents. Then we have some find and replace. Then we have something with code snippets. The last one is our file system. This is where we actually want to upload this data set. So what you can do is either by clicking this file icon with an upwards arrow, or do a right click and then press upload. Then you can, I have saved it to desktop, so I'm able to just click on this and then just press open. I already have it uploaded, but I'm just showing this to demonstrate this to all of you. And then click open, and then it should, within a matter of seconds, the data set will be uploaded. Let me just make sure everyone is good. Okay, I see some thumbs up, so I think we're good to go. So now that it's uploaded, we know that the data location within this Colab notebook is actually in content and then the name of the file. So in this file system, it's actually in this sort of larger directory called content. So before we actually can load it, we have to make sure that we're in the right location in our entire directory so we can actually access the file. So one way to do that is to check which folder in this notebook that we're currently in, and we do that using pwd. So you can either click this play button, or you can press Command Enter or Control Enter, depending on if you are on a Windows or a Mac system. And so as you can see, it shows that we're in content. And then from there, we can do the ls command, which actually will list out everything that is within this content directory. And so we see our sample data, which is here, and then our CSV file is what we need. So that confirms that we are indeed in the right location. So now we can go ahead and load the data set. Before we load the data set, we do have to make sure to import pandas as usual. This is how we read in any CSV files, and we will be using pandas throughout today's notebook. So let's do this, let's run this import. And then we're going to be loading in our CSV file, and we're going to be naming it house, just so it's we can easily remember it and it's easy to refer to. So it's loaded in, and we can do house.head, which basically will display the first 5 rows. And then you can also just run this cell, which is house, and it'll actually display everything. Obviously, it is more than 1,000 rows, so it actually won't display everything, but it will display the first 5 and the last 5. So you can see here that we have all of these different columns. We have 11 columns. So we have lot area, overall quality, condition, etc. And then these are essentially all of our different features. And then our last feature is actually this above median price, which is essentially the output that we're trying to predict. And then these 1,460 rows are basically 1,460 different unique data points. And then we will be converting it to an array, and that just makes it easier so that it's easier to process. So in order to convert it to an array, we can just store the values of our house data frame by basically accessing house.values and then setting it equal to this new variable called dataset. So let's do that. And then, all right. And then before getting into any data pre-processing, we actually just want to get some more information on our data set itself. So as we have done in past notebooks, we're basically going to print out the number of rows and columns. We did see this up here with the number of rows and columns, but just to get sort of a readout like this. And then with house.describe, here you can see all of the different columns, and then you can see the count, mean, standard deviation, max. This is really important for numerical values if you have those in data sets, but sometimes you have data sets that have more qualitative features. So this kind of information is actually not very valuable. But this kind of just gets you a sense of what are the different mean values for all of our 10 different features that are our input features. And then the same goes for our above median price that we see here. And then one last thing we can do is .info. And so if you run this, you can see that it'll show us that we have these 11 columns, and then basically we'll print out the number of non-null values. So that basically confirms that we have no missing values in our data set. And then this column shows the data type, and this is all int64, which is what we would assume given that this is what the values look like. And the last thing is basically checking if we have any missing values. We already got that confirmation up here, but this is just another step for verification. So you can do that by doing .isNull.sum. So it basically sums up the number of values in any of the values in this entire data set that are null. So if you run that, you can see that every single column has a 0 assigned to it, meaning that there are no missing values. This is fairly uncommon for real world data sets. So that goes to show that this is a pretty good data set. So that's nice. We don't have to worry about filling in any missing values or dropping any values. So that's nice. So given that, we can now get into some pre-processing. So we're going to now split the data set into our input features and the labels that we wish to predict. So the input features are going to be X, and we're going to basically be taking the first 10 columns. And then for Y, we're going to be taking the last column of our data set. And so after splitting it into X and Y, we will now be normalizing our data. And this is very important because we want the input features to be on the same order of magnitude. And this does help to make training easier, which comes in the next few steps. And in order to do this, we're going to be using a min-max scalar from scikit-learn. And this basically scales your data between 0 and 1. And this is a very common practice. Normalization is very important. So in order to do that, we do need to import the proper packages from scikit-learn. So that's from the pre-processing. And then as I mentioned, we're going to be using the min-max scaler. And so we basically are taking the min-max scaler. I'm basically just assigning it this new variable just so we can refer to it down here. And so our X scale is basically going to be calling this normalization on our X variable, which was up here. And our X variable, as you remember, is our 10 input features. So when you run that and then print it out, as you can see that everything is now on a scale between 0 and 1, as compared to how it looked up here, where everything was on different values. Some things range from 0 to 10, some things went all the way up to 11,000. So now everything is on the same scale, and it's a lot easier for our model to now train and then to predict the values as well. So lastly, we also want to set aside some parts of our data set for a validation set and a test set. This is also very common practice. In order to do this, we will be using the function train test split. And so scikit-learn allows you to do this very easily. So first we need to import that so we can actually use it. From there, what we're going to be creating is xtrain, xval, and test, and then ytrain, yval, and test. So basically, xtrain is our training, basically our training subset for all of our input features, and then our xval and test is our validation and test subset from all of our input features. And then the same goes for our ytrain, which is the training subset of our output feature we're trying to predict. And then our val and test, same thing, validation and testing subset for our one value that we're trying to predict. And then we call our train test split on our X scale and then our Y, since we actually want to, we want to make sure that we use the input features that have been normalized. And as you saw, the Y was already fully normalized, so we don't have to do any sort of normalization there. And then this test size here is basically saying that of our entire original data set, basically 30% will be going into our test subset, and then 70% will be going into our training. This is typically, there's different values people typically choose. Sometimes you do 80 and 20, sometimes you do 70 and 30. Sometimes you can try out multiple and see what works best, but today I have just chosen to do a 30-70 split. And then here we have, again, we have our xval, xtest, yval, and ytest. And basically from our xval and test and yval and test that we already declared up here, we're going to be doing a further split between both of those, because from our 30% of values that were taken from the original data set to be validation and test, from there we want to do a secondary split of, again, 50% between the two of them, of validation and test. And we apply that to both our input features, or X, and then our output feature, which is Y. And so that's specified by doing this 0.5. So that basically specifies a 50-50 split. And so I'm just printing out everything here so you can kind of see what do these new dimensions look like. So as you can see, our X train now has a shape of 1,022 and 10. So basically our 10 input features and then around 1,022 input, basically different unique values for each of those input features. And then our validation has 219. Again, all of the X will have a 10 column, and then all of our Y will basically only have one column. So that's why you don't see a second value here, because it's basically just one long list. There's no more than one column for all of our new arrays that refer to the single output feature. So now we have all of our data, original data, split into the corresponding categories of what we need. And so now we can actually build and train the neural network. So there's lots of different libraries that are out there, lots of different things that people use. What I've chosen to use is Keras. There also is PyTorch and a few others. but Keras is, I think, the most user-friendly, especially if someone's very new to neural networks. It's what I used myself when I was first learning about them. So I've chosen to use that today. So in order to use Keras, we have to make sure to import the proper code. So what we'll be importing is dense and sequential, which are basically the different kinds of, so dense refers to the kinds of layers that we'll be using for the neural network. And then sequential is basically the kind of model that we're going to be using. So let's make sure to import that. So as I mentioned, we will be using the sequential model. And that means that we need to describe the layers above in a sequence. And so the neural network will basically have these 3 layers. And this is something that the user can sort of decide how many hidden layers do you want, how many neurons in each of the hidden layers, what kind of activation function. This is all defined by the user. So I have defined these, and this is kind of a pictorial representation of what that looks like. So as you can see, our input layer here is basically of a size 10. And that size 10 refers to our 10 input features that I referred to. So if we scroll on up here, these 10 columns that you saw here, that's basically our entire input layer. And that basically has a size of 10 for that input layer. And then we're going to have 2 hidden layers. So layer 1 is going to have a size of 32. And then the second one is going to also have a size of 32. Sometimes people can choose a very, an even simpler neural network architecture and just have 1 hidden layer. But I've chosen to have 2 in this case. And then finally, our output layer is just going to have 1 neuron, since we're basically just predicting 1 value. And it's going to have a sigmoid activation. Whereas for our 2 hidden layers, we had the ReLU activations. So now, as you can see, going from here and then translating to how you actually code it, you really only need 1 line of code to basically tell Keras, okay, this is the architecture that I need. So we know that it's a sequential model, so that's why we have it enclosed in these brackets here. And then we basically have our different layers declared here. So our first, this is our dense layer. This 32 refers to our 32 neurons for our first hidden layer. And that is basically our ReLU activation. And then our input shape, as I mentioned, is going to be 10, since we have those 10 individual features. Then this is our next hidden layer, again, 32 neurons, and then we have the ReLU activation. And then lastly, we have our output layer, which is going to just have a size of 1, and then a sigmoid activation. So as you can see, it's really nice that just with 1 line of code, you can basically declare the entire model. And this is, that's why I think Keras is really nice and friendly, because if you were to go back and change, maybe I want maybe 20 neurons, or maybe I want to change the activation, or maybe I want to add another hidden layer, it's fairly simple to do that. And I would recommend definitely going in and playing with this and seeing kind of how do the values change when you add more hidden layers or you add more neurons into the individual hidden layers. And I think it's really neat that you can do that in such a straightforward manner. And so now that we've got our architecture specified, we have to find the best numbers for it. So basically optimizing. And so before we start our training, we actually have to configure the model, and we do that in 3 ways. The first is basically telling what algorithm that we want to use to do the optimization. In this case, we're going to be using stochastic gradient descent, and Sneha went over this. This is a fairly common option that is used. Secondly, we have to tell what loss function to use. And since, so typically for binary classification, you can use binary cross entropy. So that's what we've chosen for our loss function. There are several loss functions, and you kind of choose different loss functions depending on your exact problem, or basically maybe what kind of data set you have. And lastly, you also want to tell what other metrics you want to track apart from the loss function. And here we want to track accuracy as well, because later on, we're actually going to be trying to change different values and basically trying to optimize on our accuracy. And so the way we specify these 3 values is doing this. So basically doing model.compile, and then simply what you do is you specify the optimizer as SGD, that stands for stochastic gradient descent. Then for loss, you specify that as binary cross entropy. And then for metrics, you basically just put an accuracy in here. And you can add even more metrics if you would like, but I've just chosen accuracy since we want to just be focusing on accuracy and loss for today. So let's run that code. And another great thing about Keras is that training is actually pretty straightforward. And again, we only need to write one line of code. So the function that we're going to be using is fit. So basically model.fit. And then basically inside here is where we specify all the different parameter values. So what we have to specify is what data we're going to be training on. So we basically have already set aside X train and Y train is what we're going to be training on. The size of our mini batch, so our batch size to be 32. That basically is specifying, okay, in our entire set of data, kind of taking even a smaller subset of that, and then what you basically take the entire data set and divide it up into these small batches of data, and that's how it decides to train on it. So you basically train on these individual, smaller components of the larger training subset. And then lastly, you also want to specify how long you want to train for, which is basically our epochs. And so this will basically, we have specified this to be 100. That's just one of the default values that you can choose. Again, the batch size and the epochs are something that you can definitely play around with, just like you can play around with the architecture of the model itself. You can very easily see how much the accuracy and the loss change as you change the epochs and the batch size. And how it changes depends on how drastically you change each of those two values. But I would recommend doing that on your own time as well. As we finish today's session, I would recommend going back in this notebook and sort of changing these numbers around and seeing how the accuracy and the loss change. And then lastly, also our validation data. And so we've already set aside these two, which is our X val and our Y val. So let's go ahead and run that. And you can actually see it like being trained sort of like in a live fashion. So as you can see, it's basically going through all of our epochs, and it's basically and it already completed that because we had a pretty small data set. Our epochs weren't that large. And as you can see, as we're stepping through here, you can see how is our loss and how is our accuracy actually changing. And then you can see what it ends up being at the end. But over time, generally what happens is that your loss tends to go down and your accuracy tends to go up. That's basically because the more you train your model, the better it's going to perform. But there is also a flip side to it where you can actually overfit your data. And essentially after a certain point, your loss will start to actually increase and your accuracy will start to go down. So that's what we're going to be focusing on in the next few steps. We're going to be seeing how can we combat overfitting and make sure that we're not passing that point of optimization. And then, so since we just trained the data set, now we can actually evaluate it on our test set. And the way we do that is basically calling this dot evaluate on our X test and our Y test. And we basically specify it to be 1 because we want to make sure to use that specific column. And so 1 refers to basically the second column in X test and Y test. So as you can see here, this is our accuracy, which is around almost 90%. So that's actually not too bad. But maybe that shows that, it can be better. So maybe you can have a smaller or larger batch size, or perhaps you can have more epochs or fewer epochs, or maybe you can split your data in a different way, maybe not doing a 70-30 split or doing an 80-20 split, something like that. I'm just gonna stop here and make sure there's nothing in the chat. Okay, I think we are good. So next, we're going to be visualizing the loss and accuracy. So we're going to be using matplotlib. which is a fairly nice and friendly package that helps you do a lot of visualizations. So let's first import that. And what we want to visualize here is actually our training loss and our what loss. And so the way we do that is basically we're going to be plotting our validation loss. And then what we're going to be, the first graph here is actually printing out our validation loss. And basically we'll end on the x-axis, you can see here that it's actually showing how does the loss change over the number of epochs that we have. And as you can see, there's kind of this overall downward trend where the loss is slowly going down as you get to 100 epochs. And then here we actually will be visualizing the training accuracy and the validation accuracy. So the way we do that is again referring to accuracy and invalidation accuracy, and again plotting it over the different epochs. And what we expect is this accuracy to slowly get better and better. So as you can see, from 0 to 100, both our training and validation accuracy are getting closer and closer, and sort of starts to taper off around our 90%, which is around the value of accuracy that we got. And one important thing to keep in mind is that every single time that you run this training, this single cell here, it will give you different values. Just because right now, the way we're splitting up our data set is completely randomized. So we're not specifically saying, okay, the first 10 goes here, the next 10 goes here, or something like that. It actually is randomly pulling the values. So because of that randomization process, every single time you're training, you should expect different loss and different accuracy values. So even when we're down here and we're actually getting our entire evaluation, that value should be slightly different. It's not going to be drastically different, but it might be, 0.001 difference or something. Even the visualizations that we're doing here, even those will look slightly different. So that's something that's something else that you can also do on your own time after today's session. Basically, just seeing, okay, even without actually changing the values of the batch size or the epochs or anything, you actually get slightly different values every single time that you train. And so next here, I actually have a model 2 that I've specified. And what we're trying to do here is basically force it to overfit. And since this is a larger model, as you can see, like a more complicated architecture, since we have more hidden layers, it actually will take a few minutes for it to train. But let me, as it's running, I'm just going to explain the architecture that we have here. So just like we had earlier, we basically have these different hidden layers. So we have our 4 hidden layers as compared to 2 earlier. All of these have a value activation. Again, our input shape is the same with 10. And then lastly, we have our output layer, which has only 1 neuron. And then again, the sigmoid activation. And then we have specified a different optimizer here, which is an Atom optimizer. Atom optimizer works better for different kinds of data sets and for different kinds of scenarios. And so I just kind of chose a different optimizer option here just to kind of change things up and see how does it perform differently. But we have chosen the same loss value, same loss function, which is binary cross entropy, and we've chosen the same metric to display, which is accuracy. And then lastly, we also want to specify our batch size and our epochs. These are the same at 32 and 100. Again, we've chosen the same X train and Y train values for what we want the model to fit on. And then our validation, again, is our X val and our Y val. So this is still going. It will take a little bit more time, but hopefully it can finish up. And then we're basically just going to repeat the same thing. We're going to visualize the loss and the accuracy again for both our training and validation, and basically see how does that compare to when we had a slightly simpler architecture. And what we're trying to do is force the model to overfit. And again, overfitting is when we kind of pass that point of optimization where the loss and the accuracy, the loss starts to increase and the accuracy starts to go down. And that's something that we want to avoid. Okay, so that completed. And so let's run this visualization and let's see what it looks like. So that does not look as great as our earlier graph. So in orange, you can see our validation loss. It's spiking up quite a bit, up and down. Same for our training. But as you can see, our training loss does start to go down, but our validation loss is actually what we want to focus on. So as you can see here, between 0 and 100, it does start to go down slightly, but then it starts to spike up. And in fact, it actually starts to continue to go up quite a bit after we pass that 60th epoch. And that's pretty bad. So that's what I was talking about, where we pass that point of optimization and the loss just starts to go up. And that's a clear sign that the model is now overfitting. And now we can plot the same thing for accuracy. So as you can see here, accuracy from 0 to 100, yes, overall it is going up, but especially for our validation loss here in orange, you can see that it hits this peak of maybe 90%, but then we continue training to the 100th epoch, and it actually goes down to the same value that we were at around a little bit past the first epoch. So again, our model is overfitting. So now that we know it's overfitting, we can actually address this. And so in order to address this, there's 3 different ways you can address this. You can do early stopping, L2 regularization, and dropout. So those are the 3 most common ways you can sort of combat overfitting in any model that you have. We're actually going to be just doing the last 2, L2 regularization and dropout. Early stopping is more useful if your validation loss actually has this sort of U shape to it. Since we don't see that, we won't be using that. So again, we actually will be having to import the appropriate things from Keras. So we want to import dropout for our layers and then regularizers as well. And then here what we have is we're basically declaring a model 3. And this is where we're actually incorporating L2 regularization and dropout. So here we have our first layer, our first hidden layer, again, ReLU activation. And here we actually have specified some regularizers for each of these. And then even for our last output layer for our sigmoid activation, we also have the regularizers. And then what's important here is that for each of these hidden layers, we implemented this dropout. And so I won't be going into too much detail on how dropout works and all of that, but basically dropout helps to combat overfitting by only taking certain values and basically, like as it says, dropping out certain values, and it will only train on some selected portion. So let's declare this new model. And again, we're going to be using atom optimizer, binary cross entropy loss, and our accuracy metric. And then again, we can choose the same batch size of 32 and 100 epochs. And again, we're going to be training on our X train and Y train, and then using our validation data to be X val and Y val. And so this also might take some time since we have these 4 hidden layers. So let's just let that run. And again, I'll be plotting out both the loss and accuracy, just so we can see if we do, whether or not we see some improvement from model 2 where it was overfitting. So let's let that run. I'm just gonna check the chat and see if there's anything. Okay, so I see some questions in the Q&A, so let me just address those. All right, so let's see. I usually split data sets into train and test. Can you clarify we should split also into test and validation, as well as how do you choose the size of the hidden layers? Why should we use sigmoid in the output layer? Yeah, so I think generally you can just do a simple train test split of 80 and 20. But what's commonly done for neural networks is that you actually want to further split into test and validation, because your validation loss and accuracy is actually where you get more valuable information from. So because neural network architecture is a bit more complicated, than maybe a simple binary classification problem, it's highly recommended that you actually further split into test and validation. And our validation accuracy and loss, as you can see, is what we're actually printing out here, because that's that's also kind of what Keras takes in as our parameters when we are selecting our validation data to be xval and yval. And then for choosing the size of the hidden layers, so I chose 32 neurons. That is, I'm not sure if there's like a sort of like industry standard or a standard for like how many you should choose. It's you know, you shouldn't have just like one neuron or something, but also having too many neurons. You could also run into the issue of overfitting. I would say starting out with something like 10 is a very nice and simple number. And then a lot of training and working with neural networks is honestly just sort of playing around with the values and seeing what works best. And in that, you actually get to see if there's a possibility of overfitting, or even underfitting is also another issue. And so a lot of times, the way that you decide the size of the hidden layers, the number of neurons that are in there, is completely user-defined. And why we use sigmoid in the output layer, I think someone else also has this question. So as Sneha mentioned, so we generally what you use is a ReLU activation for your hidden layers, and then you use a sigmoid activation for your output layer. That's just because of how you do the different calculations. Especially for the output layer, you want to use a sigmoid activation, and then for the various hidden layers, whether you have 1 or 2 or 3 or more, you use a ReLU activation. As well as for your initial input layer, you also use the ReLU activation there as well. So I have not done any sort of back propagation. I did not include that in today's notebook just because I wanted to focus on having different kinds of models and showing overfitting and how we can combat overfitting. But that is something that you can implement. I believe Keras has a way of implementing that. But that's not something that I have included for today's notebook specifically. Okay, I'm going to go back to the notebook, and then I will get back to the rest of the Q&A. So we have finished our training here. And so now we're going to be plotting the loss and accuracy for model 3, just like we did for model 1 and 2. So as you can see for the model loss, the validation loss especially looks a lot better. And so as you can see, it does start out really high, and then it does start to taper off. But if you scroll up and look at the same thing from up here, as you can see, this was like spiking up and down quite a bit, and even sort of went up by the 100th epoch. If you compare that to what we see here, it's very nice. And yes, there are minor spikes in the values, but at least it does start to taper off, and we get down to this around a 40% loss. So it is still kind of a higher loss, but it's definitely, you know, our way of combating the overfitting is actually working. And then let's also plot this accuracy, and let's see what that looks like. So as compared to what we saw in model 2, where it was definitely overfitting, we do see this improvement in accuracy. If you remember, the accuracy from model 2 was sort of really spiky again. It actually sort of went back down to that initial value. But here, as you can see, it does start to sort of get this big spike and then starts to just taper off. And this is kind of what you want your sort of your accuracy plots to look like. And you can help to sort of smoothen this out by, again, choosing the proper way to split your data, or changing the number of hidden layers, the number of neurons that you have in your hidden layers. So that's different ways that you can sort of optimize and find out what is working best for your model. And so that concludes the coding portion. Here are some resources that I have included. This first one is basically some more information about the data set that I used. This one is basically another implementation of neural networks completely from scratch using Python. And then lastly, just sort of a nice Beginner's Introduction to Neural Networks. And both of these are from Towards Data Science, which is a really nice blog. And it has information organized in a really nice and organized manner. So let me just take a moment here and look through the Q&A. Let's see. Okay. So it says, are you randomly dropping out 30% of the data in each layer, or a particular layer, or the last layer only? Yeah, so let me scroll back down here to the dropout area. Where'd it go? Okay, so I think that's model 3 where we had our dropout. Yeah, so I think what would help is, let me see if I can pull something up real quick. Just give me a moment here. Let's see here. It might help to sort of understand the what we're doing with our dropout. Sorry, just give me a moment. Let's see here. Yeah, so I was trying to find some documentation by Karas on dropout, but couldn't find something that good. But basically what is happening is that since the hidden layers, the different layers that you have, how it works is basically the output of the first layer is an input to your second layer, and then the output of the second layer is an input to the third layer. So this 30% dropout that we're doing is actually applying to each individual layer. So we have our 30% dropout from this first layer that you see here. And then after that 30% dropout, then 30% of those values have been removed, and then the input that the second layer sees has that 30% of the data already dropped out. So it is sort of applying at every individual layer. And so that's typically what's done. So you can individually sort of apply that dropout to every single layer. And let me see, I think it might help to share. I was trying to find, let's see, sorry, I'm just trying to, there was something that I wanted to share about the Karas dropout, but I'm not able to exactly find it. But feel free to add in any more questions that you have. We do have some time remaining for today's session, so please feel free to drop any more questions that you have. So the primary difference between your test and validation is that both these are, or I guess it was answered, but basically you do sort of separate this from what your model is already being trained on, but your validation is actually helps to give this unbiased sort of estimate of how is your model actually performing, and after it's already been fully trained and fully tuned. So that's something that is not initially done, I would say, in more like simpler machine learning models. It's not done by everyone, but I have seen it done a lot more frequently in, you know, in the projects that I've done. In research, it's very commonly done to actually have this split between test and validation. because where you actually get your validation loss and validation accuracy is an even further unbiased subsample of your original data, and that actually will give you a better sense of how is your model actually performing. And let me see if there's any more questions. I don't see any more in the Q&A, but feel free to drop any more questions in the Q&A. I think I'll give it maybe another minute for anyone else to add their questions, but I hope everyone enjoyed not only today's session, but our entire series. I was really excited to be part of this series and working along with wonderful presenters, and thanks to all of you for attending and for having wonderful questions. And these series are not possible without our participants. So thank you so much for attending this entire series, and I hope that you all can attend future series as well that we put on. So I see a question if there's an option to drop out only one feature, and how do we do the same in machine learning? So dropping out only one feature, as in like if you don't want to drop out, I guess like all of the 10 inputs. I have not seen that being done personally. I think generally what you do want to do is sort of apply this general dropout to every single layer as you see here. If there is a reason that you suspect that perhaps a certain input feature is causing your model to not perform very well or to overfit, then that might be something to consider, of just removing that entire input feature entirely. So going up to the original data set, say that you want to, maybe out of these 10 columns, say you want to drop, overall condition or overall quality, something like that. Then you can basically just, before you even get to training the model, you can drop the entire column entirely and then train the model on just your 9 input features and then see how it works. But you can still apply dropout if you like, but just in sort of this pre-processing phase, you can entirely remove that single input feature. Okay, so I don't see any more questions. And yeah, thank you everyone for attending. I think that concludes today's session, and I hope everyone has a wonderful weekend. Everyone stay safe and healthy, and thank you so much for attending.